school day. Okay, so we left off yesterday. We kind of ran through this whole Planck idea. And P is what? Stands for what?
Pressure.
What pressure is it? Indicated mean pressure of which stroke? Power stroke. Only one that matters, right? Because is the engine producing any power on the intake?
No.
Is it producing any power on the compression?
No.
It's kind of using some. How about exhaust? It's just dragging along. There's nothing being produced. It's only 1 out of 4 times you're actually producing something. P was indicated mean effective pressure of the power stroke. And where do we get that number?
Given.
It's given. Very good. L is length of what? Length of stroke in feet. So it's inches divided by 12. A is the of the piston, and we're going to remember that it's going to be given to us in bore. Is the diameter, but we have to go bore divided by 2 to get the radius to do that. N is the RPM, dang it. I just couldn't make something a PLA. Plamp. I don't know. Oh, plars. And K is the. Told you wouldn't forget. And all of that divided by. Which is the English. How much an English horse weighs? No, it's how much work an English workhorse could do, assuming that it is not T time. IT, yes, okay. Just so we know, I don't acknowledge the British royalty either. So all its legs, yes. Well, if it was an English workhorse and only had 3 legs, we would divide 33,000 by. There you go. You're going to get to 11,000. So it still kind of coughs along. All right. All right, but let's, aside from just looking at that, go, okay, so he threw out some stupid formula. I'm supposed to figure out the horsepower. How do I actually figure out the horsepower on an engine anyway? Huh? Measure it. I've never measured horsepower before on anything. I don't own one of those.
Is there a plane dyno?
Plane? Yes, they are. We'll get to that. Type certificate data sheet tells me right on it what the horsepower is. So why do I have to look at Planck? Well, the cool thing about Planck is, and it kind of opened my eyes a little bit, is if you look at Planck, you can now figure out how you can increase horsepower out of an engine. So I have an engine, and I want more horsepower. So what's the first thing I can do with the P? More pressure. How can I get more pressure? Turbocharge. Forced induction. How can I lose pressure? Leaking valves.
Worn out rings.
Worn out. These are good. Leaking valve. Worn out rings. What else? These are excellent.
Shorter stroke?
Well, no, we're talking about pressure.
Bigger cylinder?
Oh, I thought shorter stroke would reduce the compression ratio.
Oh.
Reduce the
Yeah, but I put that under. We're going to go. That'll be the L thing then. So just in pressure. Dirty air filter.
Loose tolerances?
What's that?
Like a loose tolerance?
Loose tolerance. Well, he kind of said that with leaking rings. It won't work if you have loose tolerances in the crankshaft. Doesn't affect that. Yeah, bad timing. That's another good one. Bad timing because you can increase or decrease pressure with where the spark happens. But things that so dirty air filter, worn out rings, the leaking valves.
No valve overlap.
Well, that's a design thing, and intake, sharp bends in the intake pipe, stuff like that, right? Yeah.
What about the exhaust?
The exhaust.
Yeah.
Okay, back pressure in the exhaust.
Yeah.
Yeah, then that wouldn't let it breathe well. It wouldn't.
Yeah.
It wouldn't get in the fuel air mixture. So you have bad scavenging. Therefore, you're going to end up when it does combust, low pressure. So all the things we can do that. Okay, what about L? What can we do with the length of the stroke? You can't do much of anything. That's a design problem. You can change out the crankshaft, right? Buy new. You can't do that in aviation. Well, you kind of can. There's one engine that let you do that with. The C85 and the O200 are almost exactly identical looking engines, and the difference in the crankshaft is one. I think the O200 has an 1/8 inch longer stroke to it, or something like that. But otherwise, no. Unless you're doing some experimental stuff, you're kind of stuck with the length of the stroke they give you, right? Back to pressure. We can also increase pressure by higher compression pistons. Okay, thus the difference between the 150 horse 320 and the 160 horse 320. Area of the piston. What can you do there? You can bore it out. Actually, you are allowed to bore aircraft cylinders. Like Continental goes 5 thousandths over. You're not going to get much. You want to do the horsepower calculation on 5 thousandths of an inch? It's yeah. So 5. Some go to 10. The most I've ever seen is 020 oversize. You're not going to get a lot of. It's not worth it. And furthermore, you bore through the nitriding, the hard coating of the cylinders, and so. But you can. But that's more just to get wear out.
When you bore a cylinder in an airplane, will it affect, it's air cooled, so it's not going to affect the running temperature of it?
Again, you're only taking out your oversized 020. That's 10 thousandths on each side.
Yeah.
It's 2 pieces of paper. It's just not much. And only some engines would let you do that, not many. There's 10. There's also 15 thousandths over in there, but some of them are absolutely not. Okay. What about this one here? Increase the RPM. Which is to say that all I got to do is just add a little more throttle and I instantly get more.
More separation.
I get more RPM. More RPM means more. There you go. That's a huge thing right there. So you think about it, more RPM equals more power. Okay, and then K is the number of cylinders. How am I going to fix that? You're not gonna. Okay. So I thought, it'd be a great example. And I actually wrote it in pencil right here, and I'm glad I remembered to do that because I did. There's a Continental makes an 0300. So describe that engine to me. 300 cubic inch. Posed engine, okay? And this engine had 145 horsepower, which I thought they actually were 150. Maybe they make a different model. And they also make a GO 300. How many cubic? Describe this to me. Gear opposed 300. Okay. I don't have the effective pressure though. That's the only bad thing. So this one put out 175 horsepower. So what's the difference between the two? Operating speed. This one operated at a max RPM of 2,700 RPM. That's the red line. And this one had a red line of 3,250. So just between that, I could have figured out the pressure if I would have just. Oh, wait a minute. Oh, I did do it. Okay. I was like, what? I didn't know what I wrote there. So P is 141.23, I think. I think I worked it backwards to figure it out. PL length of stroke is 3.88 inches. A area of the piston, it's a 4.06 inch bore. N is the RPM, 2,700 and 3,250. The only difference, PLA and K, number of cylinders, they both are 6-cylinder engines. So if we figured that out, I didn't bring in my calculator.
Wait, what's A? That's already the area, or that's just the
Area of the piston.
That's already the area.
Yep, you should be able to verify my horsepower calculations. Did you figure out?
Yeah, I did.
45.
What are you getting?
45
45 what?
horsepower.
45 horsepower?
1.1.
Well, maybe one of the numbers. I just have them scribbled on here. Maybe one of them's wrong. Have to go back to the.
It's a very big number.
Wait,
Let's see.
what
141.23 times 12.94.
I got it.
You get 12.9. Oh, 4.06.
Yep. So you got 4.06 divided by 2
Okay.
equals 2.03. Square that. X squared
That's what I asked you earlier.
equals that times pi equals. Oops, that's not right there. What'd you get here? 12 point.
We have it right next to it.
Area equals pi times the radius squared. So it's area equals pi times 4.06 divided by 2 equals 203 times. Oops.
91.
I keep on doing it.
145, yeah.
X squared
Length
times
and feet.
pi equals. Does it get 12.9 right here? 12.9.
That's the wrong.
95.
What?
289.
You erase the 0.32 and put the other one in.
You gotta divide the RPM by 2. Just divide it by 2 and get it.
Oops.
You took out the.
I did. I put the wrong thing there. That was 0.32, right?
Yeah,
Yeah.
0.32.
0.32, and this is right. 12.94.
Yeah,
That's
that's
right.
right.
That's all right, correct?
Yeah, you were correct.
Divided by 33,000, and that equals.
145.
Equals 145. Everybody should be able to do that. Even though I screwed it up. 141.23 times 0.32 times 12.94 times 1350 times 6 equals divided by 33123 equals 143. I actually got 143.54. That's pretty close. What?
So the L, how did you get 0.32?
How'd I get? Because it's
feet.
It's inches.
yes. Did everybody get these answers? So this is just 141. This is 3.88 divided by 12 equals 0.32 because it's in feet. This has to be in feet. And the bore is area equals pi times the radius squared, which is area equals 4.06 pi times 4.06 divided by 2 squared. So that's area equals 4.06 divided by 2. Was it 2.03? So that's pi times 2.03 squared. So you square that number. X squared. That's going to equal 4.12 times pi. And that is times pi equals area equals 12.946.
95.
Kevin,
So that would be 945. Yep.
for the length, will it always be in inches and we'll convert it to feet? Like
Yep.
Yeah.
Yeah, they never give you the bore in feet.
Okay, just making sure.
Yes.
One quick question. On the,
Really? You don't always have to define the length of the question. It's okay. It may just be a question.
wait, this one, Wait,
Because really, I kind of feel like this question's already dragging out longer than a short question.
I was gonna ask, for 27.
You were gonna ask?
I still want to ask.
Okay, go ahead.
The 2700
It's a quick question, though, right?
It should be.
Okay.
2700 RPM. Why is it divided by 2? What's does the 2 mean?
Because it is number of power pulses per revolution.
Oh, okay.
So remember, one up doesn't count.
Okay.
The other one does.
Yeah, okay.
Or one down doesn't count. The other one does.
That makes sense.
All right.
Thank you.
That was a very long question. That was actually a pretty quick
That
question.
wasn't a quick answer.
Yes.
Finally.
Well, he didn't come to me and say, quick answer. You know. Yes.
So this is something we will have to remember for the FAA
I
test.
forgot to.
And my test.
Says the board.
So, yes, on both.
I'll see the
And
board.
if you've done your Q&As, you've already seen the Q&A, and you already know that they're going to ask you that.
Yeah.
But of course, you could just memorize that answer. That wouldn't be very fun for me, so I have to give it to you in a different way. So you have to know how to do it. Because memorizing won't get you very far. You got to understand. So,
Yeah, the Q&A just said what was the board.
okay.
So this GO for concrete is.
If you want to do the GO300, you would have been the same thing, but you just So if you did the math for the GO300, all you did is substitute 2700 for 3250, and you would have got 175.
Okay.
All other things being equal.
72.78.
What?
172.78.
172. Okay, I'll. What? Okay, well, got it. Thank you. All right, so we got that going down. All right, and again, if you're thinking right now, that sucked. I hope that's not on the test.
Yeah, I hope not.
It definitely will.
It is. As you notice, I don't usually give a whole lot of fluff, and when I do, I tell you, okay, I want you to know this, but I'm not going to ask you this on the test. No. But I didn't just say that. I mean, it's just like a sort of. This is on the test right here. Okay, so now we're going to talk about the different kinds of horsepower. So we have brake horsepower. Brake horsepower. This is the actual horsepower delivered. It's actually kind of delivered to the propeller. So, actual horsepower. Actual horsepower delivered. I wrote 2 engine, but that's just not correct. It's not the horsepower delivered to the engine. It's what the engine develops as an output. Actual horsepower delivered and output. Yeah, wheel horsepower. Prop horsepower, but it's not because we're going to actually talk about that. So it's actual horsepower delivered output. And how do they get this? Well, it's actually measured. It's something you measure. Let me see. Yeah, I'm going to write this. So it's measured, and it's given. It's usually given in terms of a torque. You can also get it in torque. So torque is force, which is force times distance. Force times distance. And it is expressed. Honestly, I did a whole study. I was trying to come up with a way to explain the difference between horsepower and torque. Because if you look at cars all the time, they'll express the two. Oh, it delivers, 600 horsepower, but man, it's like 550 foot-pounds of torque. And so it's like, how do those relate? I can't find a decent article anywhere that can really split it up and go, that's what this is, and this is what that is. So the best they come up with is torque. Well, that's just force times distance. And I'm like,
Would torque be pushing and horsepower be pulling?
no, I wish it would have been like that, but it. Go ahead.
That was what I found online was that torque is, the more important one. That's like the amount, that's what the engine produces, and then horsepower is what the engine produces at an RPM kind of thing.
Well, no, because you can have certain torques.
See?
I don't know.
See, okay. But remember, I think I just, rather than getting into the explanation, because I couldn't find anything that was really good, it's just torque is actually a measurement of force times distance. So it's like a lever at a certain distance pushing. And I kind of left it at that, going, well, that's just what it is. You can figure that out. It's expressed as pound inches or pound feet. Notice it's backwards. Instead of foot pounds, it's pound feet. pound-inches. As where work, if you actually talk about work, work is expressed, I'll put that, work is expressed as inch pounds or foot pounds. LBS, foot pounds. So it's backwards. So if you're somebody say, well, it's so many pound feet, you're backwards. Now they're talking about a torque rather than work, which is funny because when you torque something, it's forced. It is force times distance, but what do we say? We say, yeah, 2 inch pounds, 12 inch pounds, 96 inch pounds. So we really, as a group of people, kind of screw things up, don't we? Oops, I didn't want to put that. So I had, I should have put A right there, torque or twisting force. I'm going to put B over here. So I'm not going to ask you about this part of the test, but B. B is, all right, so how is it measured? Well, first it's measured as a torque or twisting force. It's also, to measure it, we use a dynamometer. And you've probably seen many videos of cars up on dynamometers where they put them on, put the wheels on rolling tracks. And they still do that for smog?
Not if it's OBD2 and older, or younger.
Okay.
My girlfriend's
My
Jeep
OBD2.
is a diesel, and in Nevada it had to be dynoed for smog.
Wow.
But like a diesel
I mean,
pickup
I just didn't
doesn't.
think you had a girlfriend, but.
It's the same one. They would run it at like 45 miles an hour for 20 minutes.
Jeez.
Wow. So I made fun of you last year for a girlfriend.
Yeah, you did.
I don't know what it is. He showed me a picture of his girlfriend. I'm like, dude, I didn't know you were rich. All right. Or a torque meter. Or a torque meter. I've never met her. I'm sure she's nice. Which is a prony brake. Not pony, prony brake. Yeah. It would have just made too much sense if the thing to measure horsepower was called a pony brake. But no, they missed it by just, So, all right, so it's funny. So I tell you, I have a hard time trying to figure out how to explain to you horsepower versus torque. It's not even on the FA spectrum, but I thought, wow, would it be nice to know? And I can't find it, but what I can find is brake horsepower is also measured in torque, which with a dynamometer or a torque meter and a prony brake. A prony brake, and honestly, I would love to watch this happen sometime because in my mind, I can't. It doesn't quite work for me. But imagine an engine that has a very. Has anybody seen one before? I can picture it on an electric motor. It makes sense to me. And so it's a very large, polished drum. Very.
Like a brake drum?
Yeah, but the outside is very smooth. And then you put a belt over it, and then you tighten this belt with a pressure meter, and when it stops the item or how much pressure it takes, that tells you how much horsepower. So I think, well, wait a minute. So if you tighten this thing up, do you know, Alan? If you tighten it up until it stops, or even if you tighten it up a little bit, this belt, and you watch the RPM drop, what happened?
It's a load.
But if your RPM dropped, what happened to horsepower? You just lost horsepower. So I don't know. Maybe you just do it till you see a loss of horsepower and go, well, it was that. I don't know. But anyway, they use a prony brake to measure that stuff. I don't have a picture of a prony brake, but that's how you measure it. But anyway, what am I talking about? Brake horsepower. And how do you come up with brake horsepower? Use a prony brake. All right, so that's how we figure out brake horsepower. I'm going to say that's where brake horsepower came from. Then, aside from brake horsepower, we have something called friction horsepower. And the easiest way to, and I've already told you friction horsepower. I didn't put this in my notes. I should do this. It's actually a loss of horsepower from engine friction. Engine friction. Such as the rings going back and forth, gears meshing, things like that. So we have two things. We talked about indicated horsepower, right?
Yeah.
Okay, what was indicated horsepower? Indicated horsepower. What is that? Okay, so it's theoretical. I'm going to misspell Theoretical. Maybe I spelled it right. Theoretical horsepower is, theoretical power. And we derive that from math. Or I could say maths. I don't know if you're one of those people like maths. I heard the British people make fun of us for saying math when it's actually multiple, but now that I realize it's a British thing.
They drink soda with no ice, so.
Okay, so indicated horsepower. Then we have brake horsepower. Brake horsepower is what? Okay. Actual, so I can say measured output. And then we have friction horsepower, which is horsepower lost. So if I looked at an equation, I would say indicated horsepower equals, indicated horsepower, which is the theoretical, that's as good as it's ever going to get, right? So theoretical horsepower, which is indicated, minus the friction horsepower is going to leave me with brake horsepower. So what's the most? Indicated. Purely theoretical. You wish.
Is that what is stamped?
No, the stamping is brake horsepower.
Okay.
All right, so indicated horsepower, which is the best, minus the friction horsepower, which is the internal losses, equals brake horsepower. So another way to do that is, how do you think they measure friction horsepower?
By the size of the friction area?
By subtracting the two.
There you go. So how would it be, Alan?
So it would be indicated minus brake equals friction.
Indicated horsepower minus. So you do your math, then you run it, and then you see, and then the difference between that one and that one has got to be friction horsepower. Got it? Do the math, run it, and however off you were wrong. So if I said this thing's got to put out 360 horsepower, let's be real, it's got to put out 370 horsepower. Then I run it, and I'm gonna get 360. Then I've got 10 horsepower friction loss.
Like circuits?
Like circuits? Like the circus?
Electrical, how they're all like, how to match the total
Power loss.
electric.
Oh, circuits.
Yeah.
Yes. Power loss. Okay. Sure. It's resistance. She's over there really thinking hard, man. What? I don't know. All right. All right. Then we have one more type of horsepower. What is it? You're over here mumbling some sort of manpower. Why did that happen? Right. Yes. How much work an English man can do. All right. Thrust horsepower. All right. This takes into consideration the engine and propeller. Engine and propeller combination. It is the brake horsepower times propeller efficiency. We're going to talk a lot more about propeller efficiency in the next 8-week class, but to tell you that propellers are not a horribly, you're going to see, you're like, wow, how does it even work at all? So propeller is actually figured out, and they stamp it with some numbers, and it basically tells you that for every revolution of the propeller, it should move the aircraft forward so many inches. And so they stamp it like that and say, okay, so, but it's only got to be at a certain, especially if it's fixed pitched, it's only going to happen at a certain time. But anyway, so it's stamped that way. So if the propeller said it's supposed to move you forward, we'll just say 60 inches in one revolution, but it only went 50, then you got a loss of 10 inches. And you do the math on that, and I could do easy math. 60, and you only move forward 30, what's the efficiency? 50%. So you figure out the efficiency. So brake horsepower times propeller efficiency is going to equal your thrust horsepower. Follow that? So it takes in the two. So since props are are not 100% efficient, some horsepower is lost there. So I said, wow, I've got a Lycoming IO 360 and I'm putting out what's that, 180 horsepower, but my propeller is only 75% efficient. Then how much horsepower am I really using with how much thrust horsepower do I have left? 135, so we got 135 left. So then you have to start and think, well, if I start doing all these mods and I worry about my horsepower and I get my horsepower up and up and up, but I could have bought a more efficient propeller, which way would you go? For pop. So now we know why, without thinking too much about it, the fixed pitch propellers that don't move, they move in circles, but the blades don't adjust the angle, right? They're not as efficient as one that you can adjust the blade angle on. So that's why you go to the more expensive airplanes, go right to a constant speed propeller. Even though we call it constant speed, it's just the way we call it that. You can adjust the blade angle and make it more efficient. We call it a constant speed prop because there's ground adjustable, pilot adjustable, aerodynamically adjustable.
Is there any props that have like trim tabs on them?
No. Yeah, I've seen some that look like it, but I don't think you're supposed to bend those. All right, takeaway. Takeaway, or the so what? So what? I just made that up. All right. So what is our takeaway from some of the stuff we just talked about? Oh, I've talked a lot about all these different engines, and hopefully you just have a good overview of the types of aircraft engines that are out there, and you can now speak the lingo. Lingo? Is lingo? I don't think that's a real word. So hopefully you can speak the lingo. Yeah. Or what's the English word for that? Help me speak English. All right. So, and it seemed like you did when I said, hey, it's an O300, describe it. You did. When I said it's a GO300, you did. Is a GO300 fuel injected?
No.
How do you know? Because there's no I on it. Okay. So we covered that. But if any of the following are increased, then horsepower is also increased, which is pressure. And we decided that we could get more pressure by doing what? Okay, so higher compression ratio. What are my limiting factors? Okay, limited by engine design. Limited.
Fuel type wouldn't be one of them, right?
What?
Fuel type?
That is exactly it. By fuel design. Hey, if fuel didn't detonate, we'd be seeing a lot more higher compression engines out there. In fact, when we talk about, and I don't have those numbers with me, but when we get into fuels, and I've got some examples of some race engines out there that are running insanely high cylinder pressures. They run very specialized fuel.
For airplanes?
Yeah, race planes. Your unlimiteds and stuff like that. Let me see.
Do those fall under like home built? Or how do you-
Experimental.
Oh, that's how they get away with it?
Yeah.
Oh.
I might even, I don't think there's another. I think it's just experimental. So, all right, we got higher compression ratio. How do I get more pressure? Higher compression ratio, which is limited by engine design, limited by fuel design, so we can't just keep upping it. What else do we say? Volumetric efficiency.
Is volumetric efficiency like porting and polishing?
Yes, porting and polishing. And there are some companies that will do that to aircraft cylinders. I have never been a fan of that because running a cylinder overhaul shop, that's the first place they crack is the exhaust ports. So I always wanted much material there as I could. Yeah.
So I've heard that, like on intake ports,
Yeah.
you don't want to polish them
Mhm.
because you want them to be a little bit rough so
Yep.
you get the laminar flow,
Yep.
so it's smoother coming.
Is laminar flow the word you wanted to use? Laminar flow means non-turbulent. You want the opposite of laminar flow. You want turbulent flow.
No, I thought you wanted laminar flow.
That's porting and polishing.
Yeah, well, you want it to be rough so it creates the laminar flow with the air in the like rough pockets, so then you get smoother intake.
The way I've always read it is that the rough intake, the roughness of the ports causes a turbulence. The turbulence causes a mixture of the fuel and air. That if it was super smooth, and because laminar, like there, well, you had Phil. He talked about laminar airflow wings, right?
Mm-hmm.
So, and you know that means that it's non-turbulent. It follows the contour until a bug hits it, and then it no longer is laminar flow. So, all right. So, but volume. So, if we have better volumetric efficiency
What about inside the cylinders? Like
inside the cylinder, like the cylinder walls, that doesn't have anything to do with it. We just hone them so that there's coarseness and the ring seat. Yeah, it breaks off the sharp edges. So volumetric efficiency. Well, we could get volumetric efficiency up by porting and polishing, but as Mark points out, there is a second school of thought that says you shouldn't do that because that causes the fuel and air to not mix well, and then you don't get as good of a burn. So two schools of thought. But that's limited by, that's our intake design. Is it long pipes? They're short pipes. They got a lot of bends to them.
They're limited by intake design?
We could say that.
Well, I'm just trying to figure out because it just says volumetric efficiency, intake design.
It has to do with the intake design.
Oh, okay.
We could also, I thought about, should I put limited by intake design? It has a lot to do with intake design. And I also said it has to do with dirty air filters. Also have to do with how big the intake valves are, valve duration, how long it's off the seat. What else can we do? We have pressure, we can increase. That's P. What comes next?
Length of stroke.
Length of stroke, that's supposed to be increase. Let's try 2. Increase. So length of stroke and bore, those are two things I can put together to say increase engine displacement. Which is to say increase bore or stroke. And how am I going to change you one of those? I'm getting either new crankshaft, which wasn't approved to be in there, or bore the cylinders over, which in aviation you don't bore them over that much. All right, so that was PLA. What comes next?
How hard would it be to get away with putting a different crankshaft in an engine?
It's not hard under some circumstances. So first of all, you'd have to get a matching engine. So like I said, I'm pretty sure it's the Continental C85, which is the old version, because you know it's C and 85 means what?
85
Horsepower. Okay, so the C85 had 85 horsepower. The O200 looks just like it. There's also a C90 in between. But the O200 looks just like it. Then the C85 cranks are becoming really rare and expensive. So there was an STC that you can, if you have an 85, you can use an O200 crankshaft. And I believe the difference was an eighth of an inch, and it actually gave you that horsepower. So it was really kind of turning it into an O200.
So
I could be off on those numbers,
it's,
but
it's very limited on changing the crank.
right. And then I look at all the other engines out there. Well, I can't really think of very many out there that that option was there, where there's an engine that's almost just like it, but short of horsepower. Like I told you about the Lycoming 0320, but the difference there was not a crankshaft. They used the same crank, they just had different pistons. So same crank, same rods, different pistons. So there's no crankshaft changing there. And so I can't think of a single example after that where there was just a slightly longer throw.
470 and 520s, those are two.
Bores, much different bore. Because think about it, you're talking about displacement. 6-cylinder, 470 cubic inch displacement versus 520 inch displacement. It wasn't in stroke. It's a much bigger bore. It's a 5 1/8 down to 4. I forget. Yeah.
Are any aircraft engines interference engines with the valves and pistons, or do they keep them non-interference for?
I think there are because there's different piston designs, and some of them are carved out. So I do think there are some interference. Yep. Okay, so increase P, L, A. 3 is N. What else can we do?
Number of pro stroke.
RPM.
Okay, increase
RPM.
RPM. Well, if we go back and think about our O300 versus the GO300, why was it geared? I said it ran at 3,200 RPM. Is that crankshaft speed or propeller speed? It's crankshaft speed. So a crankshaft is running the cylinders. So that's all run at 3,200, runs it through gear reduction, brings the prop out, and it turns the prop, let's say, the same speed as the O300. Why? Why don't we just turn the prop faster?
Because it's not efficient.
Oh, the valve train can't.
Okay, it's not efficient is really where we're getting at. A propeller starts to lose its efficiency at a certain RPM, and that RPM is when it starts to go transonic. So propeller is a subsonic instrument, or not instrument, it's a subsonic thing. If we start talking about supersonic airflow over wings, which a propeller is an airfoil or wing, you start getting these shock waves, and the shock waves then, I don't want to get into a whole lecture on that, because Phil will do that, but you just can't have a normal wing go supersonic. And what happens with propeller, it goes supersonic, you start breaking the sound barrier at the tips, and you start losing from the outside in the efficiency of the propeller. It starts going away. Not only that, it sets up shock waves that can actually cause the propeller to crack and come to pieces.
Propeller and part light.
Yes.
What about change the pitch of the propeller?
Okay, so that doesn't help. It's still, if it's going supersonic, so you have to think about a propeller, the longer it is, the faster the tip has to go around, the faster the tip speed. So they go supersonic from the outside in. So it's got to be in the subsonic range of 0.9 Mach. I don't think you want to go for 0.9 Mach on a prop.
Like 0.72 or something.
No, I don't think it's lower than that because commercial aircraft are flying that high. But I could be wrong on that for props. But it's got to be. It can't go into the transonic range. So anyway, I tell you that to say, okay, the RPM of the engine is limited by the tip speed of the prop. So every time we say, well, why can't you turn the engine faster? Because tip speed of the prop. So there you go. There's your limiting factor. So most aircraft, I've never seen a prop RPM go over like 2,800, 3,000. Yeah.
I have a question.
I figured that's why your hand was up. Is it a quick question? You want to throw that out there?
On the outside, it spins faster.
Yes.
But I was thinking of last year with Phil, gyroscopic precession on the inside will always spin faster on the outside. Like
That's the angular velocity, not the
Yeah,
actual
yeah.
velocity.
Okay, thank you. I don't know where he's
I
going
was
with this.
thinking like if an item spins faster in the middle than it does on the outside.
It doesn't do that. It spins faster on the outside. See, the problem with you guys, like your generation, is you never got to go to the park with the deadly merry-go-round. See, like Alan and I, we're still alive because we figured this stuff out.
That's what little brothers were for.
That's right. And so we had these merry-go-rounds, these steel contraptions, and with a huge bearing, like this, and the things would go really great. And so you'd sit on it, and you'd realize if you sat in the middle, you were fine. But the more you started going out the outside, the more you have the centrifugal force and puke, right? Now, what you need to do is you need to go on YouTube, and you need to look for the one where the guy takes his motorcycle and puts it on the side.
And you will watch a literal death.
Yes. Okay. So increase RPM, but that is limited by propeller. We'll say propeller tip speed. and efficiency. Or we could always increase the number of cylinders. Increase the number of cylinders. And that is like what Lycoming did when they had the 0360, and they added 2 more cylinders, and it became the 0540. Just welded 2 more on the back. Yeah. Which also increases the number of power pulses per minute, and on and on. All right. Do you